Hello, this is the last part of the 2014 Oxford PAT. This is the long physics questions. There's probably going to be two of them because that's what they've done for the last couple of years. So we've got a question about total internal reflection, optical fibres and refraction. So we can assume the refractive index of glass is larger than that of water and of water is larger than that of air. Okay, fair enough. Explain what is meant by the phrases total internal reflection and critical angle. You are encouraged to use a diagram to explain your answer. Right, so I might even use two diagrams, although two pictures in one diagram. Maybe that's what we're thinking about here. So let's do something that isn't doing total internal reflection. So that's our normal line. We've got, that's going to be our theta r, that's going to be our theta I. I normally do these as dotted, actually, the normals. So let's say that is less dense. So we're going from dense to less dense. So the arrows are going that way. So that's our incident angle. It's going to bend away from the normal as we go into the less dense. It's going to refract that way. So we've got that. So we can say something like refraction when moving from more to less dense, so you put this in full sentences, means that the angle will increase, angle from normal will increase. So that's what we want, as in theta r is greater than theta I. Then you can say at the critical angle, let's call that theta I equals theta c, then the refracted angle will be, theta r will be equal to 90 degrees. And then beyond this, so we've said what critical angle is, beyond this, i.e. theta I is greater than the critical angle, no light leaves the denser medium, which means total internal reflection. Medium, which equals total internal reflection. Excellent. So that's part one. Derive an equation relating the critical angle and the refractive indices of two materials N1 and N2, where N2 is less than N1. So N1 is our, this is our more dense. So this is more dense. This has got higher refractive index. So we're saying that N1 sine theta 1 is equal to N2 sine theta 2. And we've got that well, if we've got a critical angle, that's what we're trying to do here. So we'll say N1 sine theta c is going to be equal to N2, because our theta 2 will then become 90 degrees. So sine theta c is equal to N2 over N1, which means that theta c is then going to be equal to sine to the minus 1. Well, we don't really need to have done this last bit. It doesn't say make it the subject. It just says an equation relating them. So we could just stop at that point and that'll be fine. So that's all good. They've started us off fairly kindly here. Right, it looks like it's kicking up a notch. Optical fibre is usually made of two materials, a core and a cladding. Okay, so yeah, we've got the core, we've got the cladding. Yeah, wonderful. Light may only be transmitted along the fibre if the incident angle of the light is less than some theta max. Right, by using your expression from part B and Snell's law or otherwise, describe an expression for theta max in terms of the core and cladding refractive indices only. Okay, so we said on the first bit, so we've already said that, what did we have? We had that sine theta c was N2 over N1. And that's our, well, we have to have the more dense one on the bottom, otherwise that's not going to apply for sine. It won't be in the range of 0 to 1 on that, so we can't have that. Right, let's draw out a better picture on this. So what have we actually got happening? This is now gonna, we got two normals. So as we're yeah, as we're coming in then, right, we're going to have to zoom this a little bit, that we've got a surface there and a surface there. If we're thinking this is the core that we've got here. So as we come in, I'm going to have to exaggerate it a little bit, I think, in order to make this drawable. So we're coming in there at this theta max, but we're moving from less dense to more dense. So it's going to refract towards the normal. And then it's going to come up here and it's going to hit, what do we need? So the maximum, we don't want it coming out the other side. So this must be the critical angle here in order to get, well, I suppose, going parallel or coming back in, whatever way you want it. This has got to be our critical angle in order to make this work. If this is less than the critical angle, we'd end up going into the cladding. So we can't have that. Now in this case, the cladding is going to have the the lower refractive index. That's what we need to have there, because otherwise this isn't going to work. So that's going to have to be n clad over n core. So sine theta c, because it has to be less than 1, that's going to have to be n clad over n core. So we have to have that. Did I actually say anything about? No, I didn't say. It's just assumed, didn't it? Yeah, we were talking about you have to be going from more dense to less dense if you're going to get that total internal reflection. So we know it's got to be that way around. Now, what are we now doing? That's for our theta c. What have we got? So how are we going to relate that to theta max? Right, this is 90 minus theta c. So we can say from Snell's law that n air times sine of theta max has got to be equal to n core times the sine of 90 degrees minus theta c, which is n core of cos of theta c. Right, so that doesn't seem too bad so far, maybe. But what are we trying to do? We've got sine c, so we're going to have to flip this over and say that that is n core, let's use our trig identity, square root of 1 minus sine squared theta c. So we need to do that because we got sine theta c, we don't have anything with cos theta c. So what on earth are we trying to do here? Derive an expression for theta max. Okay, so what are we left with here? So sine of theta max is going to be equal to n core divided by n air. Yeah, that's all good, isn't it? N core divided by n air. But we've got this square root thing happening here. So we've got a square root of 1 minus n clad squared over n core squared. Okay, so rapidly running out of space on all of this. Right, scroll down a bit more. Right, these cores are going to cancel, aren't they? So, but let's not jump ahead because I've done this in the past and end up getting my fractions messed up. So it's got the square root of n core squared minus n clad squared over n core squared, square rooted. Right, so we can now get rid of that with that. So that is going to leave us that theta max is going to be inverse sine of, well, just that square root bit, n core squared. It was weird to know where to put the squared when you've got such a big subscript on the thing. N minus n clad squared over n air. Right, that's quite an involved function, but yeah, that seems to have gone through okay. We just have to put in that trig identity, which makes it look a bit like a mess, but otherwise it was relatively straightforward, just following on, providing you got your clad and your core the wrong way round, the right way round, obviously the wrong way round. yeah, you have to make sure you've got those correctly oriented. Because, you know, we had this from this N2 over N1, so they told us, where were we, all the way back here, that we were moving into N2 from N1. So we got the same thing here. We're moving into clad from N core, or well, to the point we're not moving into it, but we're trying to. So that means we have to have N-clad on the top. So providing you've aligned this answer here to part C with what they had said in part B and what we'd talked through, then you'll have your refractive indices the right way up. Okay, in an experiment, light is transmitted along the glass fiber before leaving in a perfectly vertical end. Right, okay, this is all perpendicular. A screen is placed a long distance away from the end of the fiber and a uniform circular spot is seen as shown above. Okay, right, so we've got this screen and we've got this spot here. This is the uniform circular spot. It's going round in a circle, you know, because they're drawing it on a flat screen here. So a small glass tank containing water is placed in front of the beam so it perfectly touches the end of the fiber. You may assume the tank is parallel to the screen. Sketch how the extent of the screen, the spot on the screen changes. Okay, so they're putting a tank, a small tank. Right, so we're just putting some water here, pretty much. Okay, that's meant to be vertical, so everything's parallel. So as you go into the water, it's not going to refract as much. So we're going to get less of a change here. This is going to be a bit flatter. It's still going to refract. Really hard to, I'm going to have to draw this out again because, yeah, we really can't see it here otherwise. So we're going to have, we've got the end of the fiber. That's meant to be vertical. We've got the tank, which is also vertical. So rather than our original line, which is doing, how did they draw it? Did they draw it from a single point? Okay, they had it at a width. So it's coming here. So our original line was just going straight out, something like this. We're now going to be going less than that. It's going to be coming a bit more like this, but we're going to end up going parallel to it. Because if you end up in the same medium, it doesn't matter what you've got in between. You know, this is like drawing ray diagrams going through lenses. If you end up in air, they're going to end up parallel because you're in the same medium. And this will go a bit narrower and then parallel. Yes, again, it's really hard to draw this on the screen. So this is what's happening. These are going to be parallel. You're going to end up with a smaller spot on the screen. So you're just wanting to show that this refracting less in the water. So it's going to narrow. It's going to have a narrowing effect. It's like putting a lens of some variety in the gap. So that's fine. I mean, hopefully my description made more sense than this crummy picture that I've drawn up here. But they're yeah, it's just narrowed the spot. I mean, it's not that complicated. The tank is kept in place. Now white light is used instead of a laser. What will the image look like now? Okay, well, so if we've got white light, you're going to get different refraction based on the wavelength. So we're saying that refractive index is a function of wavelength. So refractive index depends on wavelength. So that means we're going to get a rainbow spot. We're going to get rainbow fringes around this spot. So we get rainbow fringes around central white spot. And the center is still going to be white because everything that's going straight on is just going to stay straight on. So we're going to get rainbow fringes around a central white spot. So that's what's going on there. Right, great. Yeah, so that's that one. Have we got any more bits to this question? And no, we haven't. Right, so that's the end of that one. This must be the last question. Looks like some standard mechanics. We've got two masses, M1, M2, connected by a massless, non-extensible string. Don't we always? Massless pulley attached to a table with a hole in the middle. Right, so that's just describing what we've got there. Assuming no friction, derive an expression for the acceleration of the masses and the tension in the string. Right, okay, fair enough. So let's put in acceleration going that way that way. I mean, it's not going to suddenly go upwards, is it? So we'll have that. We're going to have tension. We're going to have tension. So we're doing 2 lots of F equals MA on this. Oh, let's put the weight in. So we're going to have an M2G going down there. So M2G minus T equals M2A. And we're going to have T equals M1A. So we can add them together, which means we're going to get the acceleration is going to be M2G over M1 plus M2. And T is then going to be equal to, well, it's M1 times that. So M1, M2G over M1 plus M2. Right, that was an easy starter for 2 marks. Now what have we got? Now, and for the rest of this question, consider friction acting on the table but not on a pulley. Friction force F friction is proportional to the mass's weight. So the friction is equal to mu S mg or mu d mg, depending on whether the mass is at rest. Oh, right, so they're bringing in static friction and dynamic friction. Okay, both coefficients are known. Derive expressions for the acceleration of the masses and for the tension of the string. What condition needs to be satisfied for M1 to accelerate? So if the acceleration is equal to 0, then we can say, well, not a lot is really changing here. We've got the tension is going to be equal to M2G. That's for the one that was hanging down. That was our MT. So yeah, it's not moving, so they're just going to be the same as each other. And then for the other one, we would have that the tension is going to have to be less than or equal to so this would be static friction because it's not moving. So mu S M1G. Okay, so that means that M2G has got to be less than mu S M1G. Cancel the G's. So this is our condition for there being no acceleration. So therefore, acceleration means that M2 is going to have to be greater than mu S M1. What else did we need on this? Derive expressions for the acceleration of the masses and the tension of the string. So in that case, so that's one pair that we've got here. Acceleration is 0, tension is that. Then, but we've also got, if the acceleration is greater than 0, then we're back to the original ones. We've got the M2G minus T is equal to M2A, and that T minus now M dynamic M1G will have to be equal to M1A. So we've now got, I can scroll down a bit and I've written those out. Again, we can combine these things. The acceleration is always the easy one. So we can add these things up. We're going to have M2G minus mu d M1G divided by M1 plus M2. So, okay, you could factorize the G, but can't be bothered to write that out again. So that's A. And then T is going to be, which equation do I want to use out of these? I'm going to use the top one, actually, because it doesn't have another mu d in it. So it's going to be M2G minus M2A. So that is going to be M2 times M2, well, let's put the G there, M2G, where was he? M2 minus mu d M1 over M1 plus M2. Okay, that's good. So we got a bit of factorizing we can do on this, haven't we? We got M2G, which is going to be, let's now take the M1 plus M2 outside. So we can say that's M1 plus M2 minus M2 plus mu d M1. So what have we got on all of that? So that cancels with that. And we can take the M1 outside and left with a 1 plus mu d. So we got M1 M2G over M1 plus M2 multiplied by 1 plus mu d. that's a bit of a mess, but it wasn't very hard to work out. So that's good. What are we doing now? The table on which M1 is resting is, oh god, right, it's now rotating about a vertical axis going through the middle of the table with angular speed omega. Assuming that the object with mass M1 can be treated as point-like, derive expressions for minimum R and maximum R so they don't move radially. Right, let's go back and remind ourselves. It's going through the center of the table. Isn't that where it's hanging down? Yeah, the hole in the middle. Right, so we're rotating about this mass hanging down. So that this mass isn't going to be rotating at all. The mass hanging down is staying stationary, and we're rotating this other mass around it. So we don't have to worry about anything to do with M2 rotating. That's just out of the picture completely on that. So that's good. Right. What are we doing then? What are we doing? So if we're rotating about that, what's going to happen if we've got small, what are we doing? So, well, let's think we're getting this the right way around. So our force is going to be mr omega squared. That's our F equals ma. That's our T. So if we've got a small r, we're going to have small t, which means that M2 will fall downwards because the weight will dominate the tension. If we've got large R, we'll have large T, which means that M2 will go upwards because the tension will now dominate the weight. So that's what we've got on this. So if we want to have R min, so for our smallest R, that means we're going to be the mass on the table will be slipping towards the hole. So, but at that point, we're going to have T is going to be equal to M2G because we're still in equilibrium. We're saying, you know, we're at that point of slipping. We're at that point of everything falling down through the center of the hole. So we've still got equilibrium for M2. And for M1, we're going to have T, so friction's going to be going outwards because it's want to slip inwards. So we're going to have T minus M1 G mu S. Yeah, that's our static friction. So that means we're going to have, that's going to be, so that's our net force, which is equal to M1 R min omega squared. Right, that's our F equals ma for each one of them. So yes, we have to have a negative friction going opposed to the tension. That's right. So we can now solve this for R min. We combine them. Well, we need to get rid of the T's, don't we? So we can just put the M2G in here and then divide by M1 omega squared. Well, this just falls out immediately. So we can factorize the G and have M2 minus M1 mu S and then divide that by M1 omega squared, and that is our R min. Super speedy. The only thing that's going to change then for R max is the sign in the second equation. So for R max, because the thing hanging over the edge is still, nothing's changed as far as that's concerned, the tension's still the same, but now we've got a T plus mu1 m1 g mu s etc etc. We got exactly the same equation. We just flipped the direction of the friction because it's now tending to move outwards rather than inwards. So we're going to get exactly the same, except we change the sign on the inside of the bracket. Well, this is very pleasing how quickly that one's dropped out. So that was good. Right, what I got in store for us next? Oh, nothing. That is the end of it. Right, that was a nice question, that one. I think the only tricky thing about that one, you know, with the mechanics, the first two parts are just going through standard mechanics questions. Then they throw in this rotation, but providing you've got this first bit sorted, so you can see which way everything's moving, you know, put it into this T equals mr omega squared, then you can see, or at least net force of what's happening on here, you can see which way everything's going to move. So it makes much more sense once you've nailed all of this bit. You can see which way round to put the sign here, that this one's a minus and this one's a plus. And then it's just a simple bit of algebra at the end. Two very nice questions again. This has been an enjoyable paper all the way through 2014. I think this has been one of my favourites so far. There are a couple of crummy maths questions at the beginning, which were a bit boring, but the physics section's been really quite nice all in all. So that wraps up another paper. It'll be onwards to 2015 in the next one.